In the same way that you can use aromaticity or anti-aromaticity to describe how acidic a molecule will be, like we did in the previous exercise, 1812, so likewise you can use aromaticity or anti-aromaticity to figure out how easily a molecule will react, how reactive a molecule will be, based on how stable an intermediate would be in the reaction. So for example, with these two molecules, we could figure out which of these two molecules would be more likely to undergo an SN1 reaction based on drawing the carbocation intermediate produced in that reaction and seeing which one is more stable. So remember, in an SN1 reaction, the very first step is the loss of a leaving group. The halogens are great leaving groups because they're really big, so they're able to spread the negative charge out over themselves. That stabilizes the negative charge. So for example, this molecule on the left, if that bromine left that molecule, it would take its electrons with it, and that would leave a carbocation behind. The molecule on the right, a similar thing would happen. So you'd have all those pi bonds there, but the bromine would leave, and it would take the electrons with it, so you'd be left with a carbocation. Okay, so then, once you have that, the question is, are those carbocations stable? Now they're both allylic, fine, but the real question is, we have a ring with a conjugated pi system, so the stability really has to do with the molecular orbitals. If one of these is stable, then the bromine will be really likely to pop off, and the molecule will be able to undergo an SN1 reaction. It'll be there for a nucleophile to attack, but if the molecule is really unstable, then the bromine will never leave, and it won't be there for a nucleophile to attack. It won't undergo an SN1 reaction. So we'll go through our usual process of thought for these two carbocations. First, are there parallel p orbitals on every atom in the ring? And here, there are. Remember, you have to have the parallel p orbitals for the pi bonds, and a positive charge is an empty p orbital. You have to have parallel p orbitals for the pi bonds, and the positive charge is an empty p orbital. So in both cases, yes. So these rings are either going to be especially stable, aromatic, or especially unstable, anti-aromatic. The question is, how many electrons do they have in those p orbitals? Is it one that's summarized by the pattern 4n plus 2? Is it a Huckel's number, or is it not? In the molecule on the left, we have 2, 4. There are 4 electrons there in those p orbitals. In the molecule on the right, we have 2, 4, 6. We have 6 electrons in those p orbitals. So let's write out that pattern for 4n plus 2. If n is 0, then it's 2. If n is 1, then it's 6. If n is 2, then it's 10. If n is 3, then it's 14, and so on. I'm plugging numbers in to that 4n plus 2 equation. Notice that 6 is one of those numbers. That means that this molecule on the right is aromatic, in other words, very stable. And 4 is not one of those numbers. It skips over 4. It goes from 2 to 6. 4 is not one of those numbers, and so the molecule on the left will be anti-aromatic. So that's very unstable. And you can use that information to determine how likely the molecule is to undergo an SN1 reaction. If this carbocation is really unstable, then the bromine is not going to come off. Once it tries to, if it tries to come off and leave with its negative charge, this molecule is going to come chase after it. It's really unstable. It won't just let it leave. And so the bromine effectively won't leave. It won't ever be able to get away, and so you'll never have the carbocation for a nucleophile to attack, and you would never get an SN1 reaction with that. At least it wouldn't happen as easily or as quickly. The molecule on the right, on the other hand, this carbocation is extremely stable. And so the bromine is going to pop off. When the bromine pops off of that molecule, it's able to leave the molecule. What does this molecule care? It is already really stable because it's aromatic. And so it's really stable, so the carbocation will be there. It'll be there for a nucleophile to attack, and you'll get the SN1 process. So the molecule on the right is the one that will react more readily in an SN1 reaction because the carbocation that's formed when the leaving group leaves creates aromaticity in the ring. That means it's stable, that means it lets the leaving group leave, so the carbocation's there for a nucleophile to attack, and you get your SN1 reaction. So you can see how you can use this aromaticity and anti-aromaticity to predict the speed or even the possibility of reactions that form carbocation intermediates, like an SN1 reaction.